This may sound as a nonsense, at least for the first time. And I don't try yet to convince you to accept this picture of different universes literally. But mathematically, the behavior of the electron in this experiment is described as if it really takes both paths. In quantum mechanics, there's no such thing as a trajectory of an electron, or a photon, or any other small particle. We can detect and fix the points of the electron departure and arrival here, but we can say almost nothing about what happens in between. And if we try to detect the electron somewhere here, it appears that almost at any point it can principally be detected, though with different probabilities. Closer to the straight line, we have bigger probabilities of detection, while far from it, we have a very small, but not zero, probability of detection. And these probabilities are true probabilities. It is not some lack of information. The result of the electron detection cannot principally be predicted. You only can expect to detect it in some area with some high probability, but you never can be completely sure. It is really like the electron takes all these paths. And the electron detection, physicists say measurement, somehow subjectively destroy all other paths to you. I say here subjectively because the bigger picture here explains that this detection, or measurement, actually does not destroy anything. It just makes previously identical copies of the experimenter here to be not identical anymore. Now I want you to imagine that you have some classical computer, as you really do, since you are watching somehow this lecture. And this computer now is solving some important task. For example, it tries to reveal some password with the brute force search or brute force attack. And now imagine that you really have millions of computers which are absolutely identical to this one. And since they are identical, they are doing exactly the same thing. Your computer makes a try for some password like 1, 2, 3, 4, 5, and all these millions of computers simultaneously repeat this try. Is there any sense to have these other computers? It looks like there's not. But if you manage to organize these computers to make different tries, then the whole system becomes millions times more effective. This is what quantum mechanics can do for you. It can make things previously identical to be not identical anymore. And it does this with these unpredictable, truly random things, one of which is a trajectory of an electron. It may be not true, but for now it looks like true that anything in the universe is represented with many, and I say many since I don't know how many, some say infinity, many identical copies. And while these copies are identical, there's no interest in them. But when they stop to be identical, when they start to differ somehow, then subjectively we can perceive only one type of them. And the copies of ourselves stop being identical either. And we perceive this change as a random event, the truly random event. The point here is, if you have a process which is truly random, not because it seems random, but is, because of this process I tried to describe before, then you probably can extract some use of it and create a more effective computation. Now, how this true randomness is used in mathematical model? If we have this qubit thing, say in the state plus, and we try to measure it in our ordinary basis like 0 and 1, then we obtain a truly random result. With the probability 1/2, we are going to obtain 1, and with probability 1/2, 0. And it means to us, as we know now, that the qubit in a state plus is actually a qubit being simultaneously in state 0 and the state 1. This is why this state is called a superposition. It is like the qubit is in both of these states. It does not work with our pendulum qubit though. If we rotate our swinging axis in a state plus, like here, it does not mean that the pendulum now is in two states, 0 and 1, simultaneously. Because the measurement of this state is not random. So imagine we have some function which takes 1 bit as an input, and if we pass the qubit in the state plus to this function, we will make the function to compute its value on both inputs, 0 and 1, simultaneously, thus doubling our computing power. While if we pass our pendulum in state plus to our function, it will just refuse to work correctly, since we did not pass the correct input to it. Now, this is the closer look to the source of quantum parallelism. Qubit not just can store many different possible values. It can have two values simultaneously. One qubit can store two values simultaneously, 2 qubits 4 values, 3 qubits 8 values, 10 qubits 1024 values, etc. simultaneously. Okay. We see that this qubit is even more powerful thing than we thought before. It would be good to implement it. Can we? Yes, we can. All we need is a source of a true randomness. And fortunately, in the 21st century, we have these sources. We can arrange experiments with small particles and obtain random results. And the systems measuring these results will split their behavior. There is this famous thought experiment with the Schrödinger's cat. We have some source of true randomness in a black box, among with the cat. And the random result we obtain from here alters the cat somehow. In the original setup, the cat ends up being simultaneously dead and alive. But assuming that the dead cat can't compute much, we'll modify the set to produce the superposition of the states ordinary cat plus surprised cat. Imagine that the source here produces a flash with the true probability 1/2. So we have two states of the source here. There is a flash and there is no flash. And since the source is truly random, both these states are implemented simultaneously in this bigger picture, which is called the multiverse, by the way. So the cat observes this superposition state and splits to become a superposition itself. And now we have two cats with different states of the mind, able to compute twice as before. And the problem now is to collect the result of this computation. Because if we just open the box, our state would split. And instead of superposition, we will observe randomly one of these cats. Obtaining the result is probably the most difficult part. And we are going to discuss it in the next episode.